Hi everyone, welcome back to the Exactpro channel and our Python4ML Bootcamp video series. Today we'll talk about functions. You may think of a function as a black box which executes certain code. Data is needed to execute the code, and that's what programs are basically about. They transform data into other data. Data is put in and data is output. What are the benefits of using functions? First of all, you get to avoid code duplication. This makes your code easy to maintain. For example, if we have the same pieces of code in several places throughout the program, and at some point we understand that we need to introduce changes to this algorithm, then we will not have to make changes to all the places. We'll only have to do it once by applying them to a function. In addition to streamlining code maintenance, we can also make our lives easier by splitting the code into smaller chunks of code. We can name them in a way that's easy to follow and call them sequentially. So this would mean adding a layer of abstraction to our code that would allow it to be cleaner and easier to read. Speaking of input parameters, their number is not limited. If there's too much data, then it's typically put into data structures. Quite a large number of arguments can be passed to a function, but having too many of them would be inconvenient. So it's recommended to use data structures. As to data types, Python is really versatile since lots of data types can be passed to a function as input arguments without previously being defined as a specific data type. The same logic works for output arguments. Their numbers are not limited. If there are many of them, they are organized as tuples. You can, of course, organize them as other data structures, but if you're listing your output arguments, then it's typically a tuple. Respectively, the type of data that was put in is returned by the function. Let's look at the first function and the elements that it consists of. To declare a function, we use a def keyword. This is short for define. After that, we should use a space followed by the name of the function. In Python, there's a convention to use underscore to separate words if you have separate words in the name of the function. Other programming languages have different conventions for that. The name of the function is followed by parentheses without any spaces. In this case, I'm saying that I'm not going to have any input arguments because parentheses are used to declare input arguments. Mine are empty. The parentheses should be followed by a colon. Then I'm asking the display function to display the function by simply naming the function and without calling it. Please mind that there's an indent because the body of the function or the code to be executed has to be indented. In line 3, I'm basically calling the function. As a result, I'm getting the name of the function. I see that it works in a main. This is something we're not going to dwell upon in this course. We do not use this variable in Google Colabs. This is followed by a full stop and the name of the function and the parentheses to mark that it's a function. There are 3 ways to pass input arguments to a function. This means that there are 3 ways for us to pass the arguments via these parentheses. We can enumerate them as variables and use, for instance, A, B, and C, etc. Secondly, we can pass a tuple, which is basically a set of unnamed variables. Or we can use a dictionary for this purpose, saying that there will be a list of variables, but we don't know their names. The users will decide for themselves what their names will be. Let's look into option 1. Here, I'm saying that my function will accept 3 arguments, A, B, and C. And in the function body, I'm displaying these variables via the print function. Let's try to experiment. My first call follows the order in which the arguments were placed in the function. A is followed by B followed by C. And I'm passing them the values 1, 2, and 3. After running this function, I get 1, 2, and 3 as output. In the second example, I have some variables switching places, but the values remain the same. A is still equal to 1, B is still equal to 2, and C is still equal to 3. So just their order is different. In this case, the output I get has the same order of variables, so the initial order of variables prevails. The C that's equal to 3, that's in the first place here, will still be output third. The last option is not to declare which value each variable corresponds to. And in this case, the values will be attributed to the input arguments according to the initial order of variables. In the function, A goes first, so A accepts 3, B accepts 2, and C accepts 1. In the output, we're getting 3, 2, and 1 respectively. This is how this approach works. Let's now look into the tuple case. There are abundant resources talking about this asterisk. It's also not the only way to use this symbol. Although in our case, it's enough to just know that if we're putting an asterisk in before an input argument of a function, it means two things. Firstly, these values will be a tuple containing values that will not be named. For instance, in the previous case, we knew that variable a gets us a value. As a result, we can pass, let's say, 2 input arguments in this line or 3 arguments in this line. The same values are output, 1, 2, and 1, 2, 3. So here, arguments are used with an asterisk and then used as an ordinary variable. Its values will be a tuple when output. The rules that work for a tuple are applied here as well. We can get values via indexing. We can also format input arguments as a dictionary. So overall, we don't know how the user will name our input arguments, but they may be named. In this case, we declare all our input arguments as being a dictionary. Then the user calling the function will have to indicate that there's an a variable which equals to 1 and there's a b variable which equals to 2. So we don't get away with just saying 1, 2, 3, 4. We have to declare the names of the input arguments. As a result, we'll be able to get a dictionary with the values attributed to variables, and the input parameters defined by the user will be available via keys. So one will be able to iterate through them, check the existence of an input parameter, and use it if necessary. Now, let's combine these approaches and see how they work together. Here, we are first indicating that we're expecting a set of unnamed arguments, which will be a tuple. Then I'll need arguments a, b, and c, and we can add something else at the end. The correct use of this function looks like this. I've put in 10 and 20, they make up the tuple. I've put in a, b, and c, and they refer to the variables, and then I've put in d and e. In the end, I'm getting the tuple of 10 and 20, the input parameters a, b, and c that are equal to 1, 2, and 3, and a dictionary. Here, I'm first displaying a, b, and c, then the tuple, and then the dictionary. Let's experiment some more with how a similar function can be called. If I only enumerate a, b, and c, as well as one more argument, d, then I'm not going to have any values left for a tuple. We see that the tuple is empty. A, b, and c are filled. And the new argument, d, with the value of 4, has been passed. Let's now try not filling our dictionary. This also works. The dictionary will simply remain empty. So we have data for the tuple, we have data for the input parameters for a, b, and c, but there's nothing for the dictionary. One more option is to simply pass the values for a, b, and c, in which case our tuple and dictionary will remain empty. We've finally arrived at the most interesting point. If we choose to just pass 1, 2, and 3 instead of adding the a, b, and c, then we'll raise an error. When we declare a, b, and c as input parameters, we're making the user introduce the values. The user will inevitably introduce something there. They may pass incorrect values to it, but values will be passed nonetheless. At this, we're making the user think about what will be passed to the function. Anyway, the input argument will always exist. We see that the current call is incorrect. We are getting an exception with the message that required values for arguments a, b, and c are missing. So these values are mandatory elements. There's also another way. We can say that we have mandatory arguments a, b, and c, but the user will not have to attribute values to them. If the values are not attributed, then by default, they will be considered null. So in my case, I've written that by default, each of these values is equal to 0, and having called a function with 2 input arguments, I'm attributing 1 to a and 2 to b, while c remains a 0 by default. That's why my output is 1, 2, and 0. Now we're moving on from input arguments to output arguments. How do we return the result of the calculations? Return may be the most popular word across all programming languages. It allows us to get a certain value from a function. In this example, I'm adding up a and b while multiplying b by c. Python knows that we perform multiplication first, so let's see how it works. I have passed 2, 2, and 2 as values. 2 by 2 is 4. Adding 2 to it makes 6. so this entire function returns 6. And I can add 4 to this result right here. I get 10 as the overall result. So we are able to either return just the variable values or write mathematical expressions, the result of which will be calculated and returned by the function. Let's now look at this example. The exception we're getting is that we can't add up an integer and a non-type, which means an undefined data type. We have an arrow pointing to line 4 of our code, so the problem is here. It's also underlined with red. The problem is in the fact that the function itself isn't returning anything. Here we have print instead of returning. So instead of asking the function to return something, we have a procedure. A procedure also returns a data type, and that type is none type. When an error is raised, this is what it looks like. And when we try to add up none type and an integer, we get an error, because those two can't be added up. To correct this, we just have to write return instead of print. As I've already mentioned, we can return several values from a function. In this case, I'm redeclaring the function and saying that there are 3 input arguments, a, b, and c, and I need to return them in reverse order. When I'm calling a function with the values of 2, 3, and 4, I can store these values one more time, this time into variables d, b, and c. So 4 will correspond to d, 3 will correspond to b, and 2 will correspond to c. After we print this, we will have the same sequence in reverse. If you indicate one value and only store one variable here instead of 3, you will store a tuple in that variable, because essentially this is a tuple. It doesn't come with parentheses, but it is a tuple. Let's now talk about exceptions. When it comes to functions, there are 2 strategies for handling them. Exceptions can be handled either inside or outside the function. How do we handle them? Under handling, we understand writing additional code to resolve the exception. To handle an exception, the target code needs to be put in a try block. I am putting in return a divided by b divided by c. If division by 0 occurs, the program is going to display an exception, but the program will keep running. So I'm going to log this exception, but I'm saying nothing critical is happening. In this except block, we are indicating the class we are expecting. Each exception type is represented by a class. Dividing by 0 is represented by the 0 division error class. There's an extensive hierarchy including parent and child exceptions. Here you can check out the entire hierarchy and the description of the exceptions. Right now, we'll only look at several of them, which are the basic ones just to see the principle of their work. Here, I'm placing the name of the exception I'm handling and giving it a pseudonym to be able to receive technical information about this exception from the X variable. And here we display this message. Now I'm calling it. I'm dividing a by 0 and by another 0. I'm getting an exception, but it's not a red exception anymore. We're establishing that it's not critical, so the program will keep running. There's also the second strategy. We can write a function in which there may occur an exception, for example, division by 0, but if it does, we will handle such an exception outside the function. As a result, we are putting the try block just before calling the function. Calling the function happens inside the try block in this case. In this situation, I try dividing a string by another string, and division obviously doesn't apply to strings. That's why I'm handling a different type of exception, type error, which means I'm subjecting my data types to an operation unknown to them. Overall, these 2 strategies are defined inside the commands. Some programming languages may be inclined to use one particular one. For instance, Java has its own mechanisms for this case. It's your right to agree within your team what strategy to pick and on what level you're going to handle such exceptions. You can also mix and match. For example, here I'm handling division by 0 inside the function and handling a type error outside the function. Let's sum it all up. When I'm calling the function for the first time, the processing is handled inside the function by this exception. As a result, this message is displayed. For example, division by 0. In the second call, I'm passing strings instead of integers to the function and getting another kind of error, type error. That's a good example of a combined strategy. You can also indicate several errors for several error types that are to be handled. Here I'm saying that if 0 division occurs or type error occurs, display these exceptions. That does work too, and here's the output. There is another way too, such as if we need specific sets of actions for different exceptions, we can enumerate them one by one. For example, I have a dictionary and I know that the D key is missing from the dictionary. So I'm trying to get a value from the dictionary by a B key and store it into a B variable. I will get a key error exception in which I will simply write a default value for the B key and will then try to store the value from the dictionary into B one more time. The output will be a dictionary that will have this key with the corresponding value of 0. So this bit of code has worked. And in case any other exceptions occur, this bit of code will be working. So we can use it as a contingency for handling exceptions. It's a good safety mechanism. The only thing is, don't use the word pass here. If you do, the program will not inform you of any exceptions, while display does let you know about them. Please also pay attention to the fact that these ways to handle exceptions are mutually exclusive. If one was used, the other won't work, not even taking into account the fact that exception is the parent of all other exceptions. You might have read this already if you've checked out the link. It will only work if, let's say, the key error block hasn't been used. If there was division by 0 in the try block, then exception will be applied. Let's practice and try to solve a quadratic equation with the help of a function. If you have taken any programming courses, you may remember this type of task. So there's a function that helps calculate a quadratic equation, and we're passing it 3 input arguments, a, b, and c. First of all, we see a comment that's attributed to the function. It has its own formatting. 3 quotation marks mean it's a multi-line comment. This one has 1 line so far, but here's what a complete multi-line comment looks like. We can transfer text to a new line. In that case, it will start from the leftmost position with no indents, so that indents wouldn't become a part of the line. So what do we have here? It says if the a coefficient is equal to 0, then we are raising an exception. The word raise generates this exception, so we can generate our own exceptions. Please mind that this process is quite resource heavy. If you need to receive a certain value as output, it's recommended to use data structures and, in general, anything but exceptions. Exceptions are better suited for the exceptional cases. In our case, we have invalid data, and this is our way of saying that we can't use a quadratic equation for such coefficients. After that, we calculate the discriminant, then the square root, and calculate 2 values. So a tuple is being returned. Otherwise, 1 value is to be returned. If the discriminant is less than 0, then a string is being returned. So our function can simultaneously return 3 different data types: a tuple, a variable of the float data type, or a string. All of this is possible with Python. As far as the documentation goes, as a rule, when you hover over the function, the documentation pops up. In addition, we can call it via the code. For instance, I'm now calling the function and using a full stop and calling this variable if we can agree to call it that. It consists of an underscore and the word doc followed by another underscore. This is a common way to call a function's documentation. Here, we have an example of a linear function and a multi-line comment accompanying it. We're returning strings and values here and do not have any exceptions. Now we can try and test everything we've learned. To do it, we've created 3 cycles of data generation. I want to get a list of tuples, each of which consists of 3 values that can accept the values of 0 or 1. So I get 8 values that look like a set of binary numbers. Now I'm going to go through these values. So test input now contains a tuple that will be passed to a function. In the output, we can see that the test has been launched with the values of the tuple equal to 3 zeros. Let me remind you that this F letter preceding the line means that the line will contain parentheses that will in turn contain a variable. That's how this part of the line was formed out of the variable containing a tuple. Moving on to the try block. We're now passing the tuple for calculating the quadratic equation. The asterisk is needed to extract the tuple values and apply them to the a, b, and c variables. And here's another interesting use of an asterisk. It turns a tuple into 3 variables that can be passed to a function. If an exception occurs, then we're displaying a message and then trying to calculate the square root with the help of the linear function by indexes. This function is now accepting 2 input arguments, out of which we only need b and c to perform the calculation. Here are the test results. Sometimes the linear function is used. In some cases, we get 1 square root. In some cases, we get 2. In some, we get a negative discriminant. So this is a simple way to test a function. Please mind that this is a manually created test. Python has libraries that have nice visualization tools. Here, the example rather serves the point of demonstrating the collaborative work of functions and exceptions. Now for the homework. It's not a mandatory task, but it will improve your coding skills. It's based on both previously discussed material and this new information we've just covered. It includes 4 subtasks, which are essentially 4 functions that you will need to write. The point of the first function is to add a new column consisting of 2 existing columns to a data frame. So you will need to pass the function a data frame and the name of 2 columns. You will get a new data frame containing the newly created column as output. The second function should output all possible pairs of columns, so we basically send in the list and receive combinations, or pairs. This list has to be returned as a list from the function. These 2 functions are interconnected in terms that we're passing the values of 2 columns to the first function, while the second function is preparing the possible values. The third function is needed to use the 2 previously created functions. So we'll first call the first function, then set up a cycle and pass data to a new function. All of these functions should be unified, so to achieve that effect, there's the fourth function. It tells us that we need to use several data sources to get different sets of columns and make sure that our functions work correctly for these different sets of columns. So that's our task. All the functions are interconnected. They call each other and complement each other. Try your best to make them work. If you run into exceptions, feel free to add error handling blocks. We do expect you to run into some errors. For those who consider this task too easy, there's also a task of creating a function that accepts a certain value. The function itself is based on the call-its hypothesis. And we need to return 200 unique values from this function that will be generated by it. So the value suitable as an input argument has to give you a chance to generate a list of unique values of this length. That's a wrap for today. Thanks for staying with us till the very end. We look forward to hearing your feedback, questions, and comments in the comments section below the video. Hope you have fun doing your homework, and we'll see you at the final session of the Python4ML Bootcamp very soon. Bye!